about provable total empty search problems, something which is really close to my heart. And the plan for the talk, so I want to be gentle with you. So knowing that I'm the one speaking after the conference dinner, I thought I start easy. At some point, of course, I have to accelerate. So I want to start with my roots. So I want to root this talk in my heritage. So where I'm coming from and why I'm on this path. I will speak about boundary arithmetic because the provable total empty search problems will be mainly linked to boundary arithmetic, and I'm not expecting everyone to know much about boundary arithmetic, so I will give a gentle introduction there. Then speak about total empty search problems, and that will kind of be more or less the introduction, which will take probably half of the talk. And finally, give some characterizations of provable total empty search problems for boundary arithmetic. And then also for stronger theories like piano arithmetics, and then conclude with some things which I have omitted because the whole talk is tainted with my interests, but there's much more work currently going on total empty search problems, and state some open problems and challenges, maybe also related to computability. Okay, so let's start. And I start with Peano because he gave us the Peano axioms, and boundary arithmetic is very much linked to Peano. That's one of the key figures for me. Then I also want to mention Kurt Gödel. And of course, yeah, okay, you all know it, but somehow for me, the two most important things are that he gave us the completeness theorem. It's kind of obvious, but somehow if you speak to complexity theorists, sometimes the ability to be able to reason in a mathematical way about the structures which we are carrying and linking them to form a system, that's really a powerful tool, which not everyone is making best use of. So that's important for me. And the other thing are his incompleteness theorems, and I will come back to that. Gerd Gensen, because he gave us the calculus, LK, a very important tool. As a proof theorist, a lot of things are building on that. But also his consistency proof for Peano arithmetic, and I will come back to that in a minute. And finally, of course, I have to mention Alan Turing. We are here at CIE, the father of computability, but also the model, the Turing machine, is actually at the heart of complexity theory. Yeah? Without that, we would have to find something else. One could say it would have to be invented if it were not already. So that's kind of my heritage. Now, as I said, so Peano arithmetic is kind of closely linked to the way I want to introduce boundary arithmetic. So let me briefly say what it is, even though I assume everyone knows it, but I thought I'd be gentle at the beginning. So seeing something which you already know is a good start after a conference dinner. So the domain will be the natural numbers. I will use a simple language of 0 plus 0, 1 plus times and less than or equal. You could have other axiomatizations, but that will do. And then, of course, you have defining equations for those. But most importantly, we have the schema for full induction, as you all know it, for all formulas in this first order language. Then I also want to mention Gödel's second incompleteness theorem. So we are able to, so via that, it is possible to show that Peano arithmetic does not prove its formalized statement of consistency. So statement saying that you cannot derive 0 equals 1 from the axioms of Peano arithmetic. But we also have a proof of consistency from Gerd Gensen. Yeah? So if you add, you have to strengthen Peano arithmetic, and one way to do that is to add transfinite induction up to an ordinal epsilon naught. So to extend the schema of full induction to ordinals, to a transfinite induction scheme. And then if you go up to epsilon naught, then this suffices in order to prove the consistency of Peano arithmetic. So and here we see kind of consistency as a separating statement between Peano arithmetic and the stronger. Okay. Then I also want to mention a couple of things about fragments of Peano arithmetic, because that is resembled within bound arithmetic, but more classically, this was way earlier. Kirby and Paris in the 70s started to look at fragments of Peano arithmetic by restricting induction to so-called sigma n formulas. You know that, I assume. So you are looking at n alternations of unbounded quantifiers in front of something which is bounded. Can I point here? So phi is simple. It's consists bounded quantifiers will do. One could have another way of characterizing this, but for this setting it will do. And then you have n alternations of unbounded quantifiers starting with an existential. So if you have induction just on those formulas, then it is I sigma n. So they started to study those theories and consequences of that. One particular result, which can be phrased in this way, but had been done differently, is by Charles Parson, who showed, well, one can phrase it nowadays in this way, that the so-called provable recursive functions of I sigma 1, so first fragment, are exactly the primitive recursive functions. Now, what are provable recursive functions? So these are those recursive functions whose totality can be proven total in the theory. So you have to describe the function in the language of the theory, and then the statement of totality needs to be provable. And then this is called a provable provable recursive function of the theory. And that is kind of a prime example of a concept which will occur over and over again. And finally, I want to mention this result by Ono and Kadoda from the 70s and 80s, that you can characterize the provable recursive functions of Peano arithmetic, again with ordinals. You have to take the less epsilon zero recursive functions, that exactly characterizes the provable recursive functions of Peano arithmetic. So it's again a scheme of recursion extended to ordinals, and if you take that for all for any ordinal less than epsilon zero and take this as a scheme, then you get again all provable recursive functions of Peano arithmetic. Okay, so that's kind of the heritage, the context where I was coming from. So I should have said at the beginning, I'm a proof theorist, studied in Münster, ordinal analysis. So all these things around ordinal proof theory are really dear to my heart, and I always try to find ways of making good use of them in these studies which I'm looking at. Right, if you have any questions, please feel free to interrupt me. Happy to take them anytime. Okay, so then that's the first part. Next part is bounded arithmetic. So there are various ways in which bounded arithmetic can be or has been defined in the course of the years. So it actually started with Cook's equational theory, PV, where he looked for reasoning in a feasible way, as he said. So it was an equational theory, was not covering all fragments of bounded arithmetic as we currently know them, but it was definitely the starting point, looking in this direction. Then Bass, I should have said aligned to Peano arithmetic. So Bass defined bounded arithmetic as an extension or aligned to Peano arithmetic. So using that setup of Peano axioms, how could it be extended, modified, so that you get good classes? And I should have said the aim was always to relate. So we saw the results about the provable recursive functions of Peano arithmetic and fragments of Peano arithmetic. The aim was always to find something similar which relates to complexity theory. So relates to the polynomial time computable functions, but then also to fragments of the polynomial time hierarchy. Yeah, that was the aim. Cook achieved that in relation to the polynomial time computable function. Sam achieved that for the whole polynomial time hierarchy, and we will see a little bit later how that has been achieved or what that precisely means. Actually, Sam, when I asked him about that, he never aimed for that. It was a kind of byproduct. He aimed for obtaining feasible proofs in some propositional systems. That's why he set up boundary arithmetic. But out of that came this good characterization. So it was originally a byproduct. Nowadays, it's actually one of the main themes. And then I also wanted to mention this other direction where you use different sorts. One sort for the strings, another sort for indices in the string. So it's a kind of first order theory, but with second order objects in there, which makes it a bit more elegant, maybe to reason about them. But it's then, and somehow there's this book by Cook and Nguyen from 2010, which simply develops this as a whole theory. And it's very suitable to then look also at complexity classes below polynomial time. So if you want to look at circuit complexity classes, that is a really good setup to look at them. But I will stick to bus approach and relate it to Peano arithmetic and use that setup in order to introduce boundary arithmetic. So again, we start with Peano arithmetic. The domain is again the natural numbers. We had the same symbols as we had for Peano arithmetic, but now we need to add a few more symbols. And crucially, we need to be able to speak about the binary length of the numbers given to the system. That's one. But more importantly, we need this famous smash function for those who have seen it. And why do we need it? Because this exactly creates polynomial growth rate. So if you run a Turing machine in polynomial time, your input can grow polynomially, meaning that the length of the input, the length of the output is a polynomial in the length of your input. That's what is meant with polynomials. Now we want to speak about that with bounded formulas. And in order to be able to do that, we need terms which can express this polynomial growth rate. And if you look at smash functions, any finite iteration will give you any polynomial growth rate which you need. So that's why this function needed to be added to the language. Okay, so that's, and there will be a few more polynomial time computable function predicates to make the setup easy and manageable, but these are the main ones. Then we will look at delineation of bounded formulas. We saw for Peano arithmetic, we have the delineation of formula classes according to unbounded formulas, which gives us the fragments I sigma n. Here we will look at delineation of bounded formulas. And we have this class sigma b1. And what we do something similar. We count the alternations of bounded formulas instead of unbounded formulas. So if you take sigma b1, you have one bounded formula in front of something which is simpler, and simpler here means that you can quantify, but only about over sharply bounded terms. So sharply bounded means logarithmic, and I come to that point a little bit later. So that's kind of sigma b1 formulas, and then sigma b2. The next level would be you have two alternations of bounded formulas, an existential followed by universal, in front of something which is simple, meaning you only have sharply bounded formulas followed by something which is quantifier-free. Okay. And it was known at the time when Sam introduced that by a result by Stockmeyer, that those formulas classes are able to exactly characterize levels of the polynomial time hierarchy of predicates. For example, NP, or also written as sigma P1, the first level of the polynomial time hierarchy. Those predicates are exactly described by a formula of that shape. Yeah. And then the next one would be NP to the NP. So NP with allowing NP oracles, or sigma P2, that's the second level of the polynomial time hierarchy, etc. Okay, still with me? No objections. Okay, so then let's continue. So this is language, formula classes. And then how do we axiommatize those theories? Well, we need some formulas defining our non-logical symbols. That's called basic. And then we need induction. Again, we have the schema of full induction, as we have seen before, right? If you, it's exactly the same schema before, but now the formula is simply coming from the smaller class of bounded formulas, sigma bi. So that will be sigma bi induction. But more importantly, there are weaker, apparently weaker forms of induction. Namely, so I've written here sigma bi L induction for logarithmic induction. It has the same premise of induction, but you can only conclude that for all x phi of the length of x holds. Now that looks a bit strange. Why is that really weaker? Well, remember that, or I don't remember because I haven't told you, but you do not have exponentiation in this language. And in general, exponentiation will not be a total function in models. And you can actually construct non-standard models of arithmetic in which exponentiation is actually not a total function. And for those models, you would here quantify only over a proper segment of that model, where here you are quantifying over the full model. Yeah. So that gives an indication that probably this is a weaker axiom than full induction. I said probably because that's really a hard problem, and without extra tricks like going to relativization, we are not able to prove that. Yeah, and that's actually one of the main open problems in this area, as I will explain a little bit later. So these are the two induction schemes, and then we can define theories. S1, 2, the S theories are defined with logarithmic induction. The T theories are defined with full induction, and then you simply count with the upper index the amount of the complexity of the formulas which are allowed in the induction scheme. Yeah.
Sorry.
Yes.
So the second induction principle. So the point is that in non-down model, it could be that not every number is in length of a number.
Yeah.
But they are proper initial.
I just gave that as an intuition. You can come up with non-standard models in which exponentiation is not total, and therefore the length will be a proper cut.
Yeah.
So there will be it's a proper cut in the model. Yeah. So we are in that sense you are here not quantifying over the whole model. That gives an indication. You cannot make use of that in order to separate those in a proper sense. Yeah. Those two axioms, but it gives an indication of that this is potentially weaker. You can also think about, okay, how many steps do you need in order to reach such values? Here you need logarithmically many steps, here you need exponential many steps. So there are various intuitions why the second is actually weaker than the first, yeah. But they are intuitions, yeah. Yeah, okay, thanks. Any other questions at this point? So, okay, now we have the theories, we have the setup. Now let's look at the provable recursive function, or the equivalent of provable recursive functions in this setting. Provable recursive is too strong, is too general. We need definability, and we call a function, but it's very similar to provable recursive. But let me simply quickly step through it. So a function is sigma b1 definable in S12. I just give this as an example, and then more. Will explain cum grano salis how that relates to the other theories. So when is it sigma definable? Well, you need to have a sigma b1 formula which defines the graph of the function. So function is external to the theory. You need some representation within the theory. We say it needs to be given by a sigma b1 formula. So the graph of f in this way over the natural numbers is defined by the sigma B1 formula. And the main point is that you can prove the totality of the function in the theory. So S12 proves that for all inputs, there is a y such that phi xy holds. That's the main point. And okay, it's a function. You also want that S12 proves the uniqueness, but that's usually a minor thing. Yeah. The main point, the really which gives the strength here, is this totality aspect. So that's called a sigma B1 definable function. Okay, all happy with that concept? It's related to provable recursive, but it's not exactly the same. Yeah. And then the main theorem of Bass' PhD thesis from 85, published then in 86 as his book named Bound Arithmetic, is that the sigma B1 definable functions in S12 are exactly the polynomial time computable function. So in that way, we get a characterization of polynomial time computability in terms of theories and provable or notions similar to provable recursive functions. Yeah. Okay. So here are some other definability results. So we just stated the first one. So S12 is using sigma B1 L induction. The graph of the function needs to be sigma B1 definable, then you get FP. For S22, the next level, which has sigma B2 induction, L induction, sorry, you have to look at graph definability sigma B2. So you have to look at functions which have a slightly more complicated graph definition in order to get exactly the second level of the polynomial time hierarchy of functions, and etc. Yeah, so that goes really through all theories up to all level of the polynomial time hierarchy. And I'm just mentioning here that there are also, without defining them, that there are also theories which correspond to function p space and function exponential time. So they are second order theories, bounded second order theories, where you have a bounded version of sigma 1,1 in a natural way. And again, if you use L induction, you get p space. If you use induction, you get x prime. Again, the definition here, the graph definability is now of a very high complexity. Yeah? So it's sigma 1b1. Okay. So that's kind of what is known in terms of definability and relating theories to levels of the polynomial time hierarchy and classical complexity classes there. Good. Right. Good. Some further results. So you get inclusions of these theories in a very direct way. Yeah, so if you just think about this as an increasing chain, that's quite obvious from the strength of the induction, and that you can simulate full induction if you have a bit more. Okay, I don't say anything about that. So you get this increasing chain. Most importantly is that the S12 and S22, for example, they're very close. They are conservative up to for all sigma B2 formulas over each other, which means that T12 also has the same sigma B2 definable functions as S22, because they prove the same for all sigma B2 sentences. So in terms of definability, they are the same, and they are very close. That's what we know. Yeah. The most important problem, since this hierarchy has been defined, is whether it is a strict hierarchy. And that, of course, resembles a little bit the P versus NP problem, or the separation of fragments of the polynomial time hierarchy. Yeah, the analogon here is, can we show that a theory to the right proves strictly more sentences than a theory to the left? And that is an open problem, and it's believed to be equally hard than separation of complexity classes since the invention of bound arithmetic in the 85s. Now I should say, and I'm not writing this down here, I'm just saying here in passing, you get separations if you allow oracles for those theories. Yeah, so if you expand the theories with second order variables just as a free parameter in a natural way, then you can make use of known oracle separations for complexity classes in order to separate theories. And so there are various refinements and analogies which have been done there. So in that setting, you get separations. But of course, the interesting part is to do this without the oracles. Evia?
It's believed as difficult separating complexity classes, not functional complexity classes, but just
yeah, okay, that's a good point. And that leads me to my next slide, because I will make that a bit from this slide. Yeah, that's a good point. Yeah, so, but there are statements known that separations of complexity classes, not function complexity classes, imply the separation of boundary arithmetic. I'm not writing down the precise statement. So there's a little bit a gap to the levels, and that comes because we now look between predicate separations versus function classes. Yeah, but still there is a connection there that if you can separate the polynomial time hierarchy, then you get a separation of boundary arithmetic theories. And I'm not stating here the precise levels. Yeah. And there's also a converse known, namely, what if you separate boundary arithmetic theories? Would you get a separation of the of complexity classes? That is not exactly the case. Yeah. If I state it the other way around, then the collapse of boundary arithmetic theories is equivalent to a collapse of the polynomial time hierarchy, which is provable in boundary arithmetic. Yeah. So what does it mean? It means, okay, it could be, you know, let me get it right. It could be that we have, so we could have a separation of boundary arithmetic. Right. So what I want to say is there could be an algorithm for solving satisfiability in polynomial time, but you cannot reason about this algorithm in boundary arithmetic, so you cannot prove in boundary arithmetic that this algorithm collapses NP to P. So it could be that P equals NP, but boundary arithmetic is still separated. Yeah. Simply that, but it means then that the collapse functions must be so complicated that they are not formalizable in boundary. So that's kind of the connection, yeah. And then it's kind of belief whether you think, okay, we all believe, I guess, that P is different from NP. And there is kind of the belief that it should be in a natural way so that you can actually reason about that in boundary arithmetic. But, and therefore people believe that somehow if you try to separate boundary arithmetic, it's equally hard than separating complexity classes. But it's a belief, yeah. So we don't have a formal statement. Right, and then the final point which I wanted to make is that there are deep connections to propositional proof complexity. So it's another area of really active research, also initiated by Cook and Rakoff. Where people are studying propositional proof systems, trying to prove lower bounds for them in order to find a path to showing that P is different from NP intersect co-NP, or that NP is different from co-NP. Anyway, but I'm not, so this is an area which I will completely omit in this talk because I want to not concentrate on something else, but I wanted to mention it, that this is out there and that there are many beautiful results and developments going on there. Okay, so now we come to total NP search problems, and I'm, okay, my introduction takes longer than expected. Good, so what are total NP search problems? So it was initiated by Meggio Papadimitriou in the beginning of the 1990s. They are also called, so TFNP stands for total functional NP. And the aim is, so instead of having a decision problem, you are looking for a search problem which always has a solution. And then you can't really nicely rephrase it as a decision problem. Usually search problem, you think of them being equal to decision problems, but for total NP search problems, there it definitely breaks down. So what is the setup? So you have a polynomial time computable binary relation R, which needs to be polynomially bounded. So the idea is that you are given an X and you want to find a Y. It should be honest, so polynomially bounded. Any solution should be polynomial in the input. So the length of the solution should be polynomial in the length of the input. And it should be total, meaning that for all inputs, you find an output such, you find a Y such that R of X, Y holds. And then the search task is to, given an input X, find a Y such R, X, Y holds. So just a few quick examples. FP can be thought of as a total NP search problem. So any function computable in polynomial time, its graph would be an NP search problem. If you have something in NP intersect co-NP, then that gives rise to a total NP search problem. Yes, you can write X being in that language. It has an NP description with an existential quantifier. Bounded, the bound is kind of implicit in this phi. And it has a universal description, and therefore the search problem, given X, find a Y, which either makes phi true or falsifies psi, is a total NP search problem. You can always, because of this equivalence, can always find a Y. So this shows that if this class of total NP search problems would if all total NP search problems would be solvable in polynomial time, then NP intersect co-NP would equal P. And if P equals NP, then you can easily see that TFNP would, or that all total NP search problems would be solvable in polynomial time simply by querying the solution bit by bit. Yeah, so you write that down to get it. So that shows that TFNP is intermediate between FP and NP intersect co-NP. Yeah, so it's something that sits there in the middle. So Papadimitriou and co-authors also identified a number of natural subclasses of TFNP. And the defining principle for these classes is always a combinatorial lemma, which guarantees totality. Again, totality is the key point here. Yeah? So the strength of those principles is related to the combinatorial strength of the principle which guarantees totality. And here are a couple of examples, classical examples, which had been introduced early on and which have been studied since then. So for example, PPA says that every graph has an even number of odd degree nodes. So that's the combinatorial principle. The search problem would be, I give you one odd degree node, you find me another one in this graph. PPP related to the pitch node principle would be there is no injective map from X to X minus 1 many nodes. Again, I give you such a map, you have to find a collision or something showing that this map is not something, a witness that it is not a map from the intended map from X to X minus 1. Polynomial local search is the statement that every directed acyclic graph has a sink. The setup will always be that the graph is an exponentially sized object. So it's either given to you as an oracle, or it's given to you in a succinct description, let's say as a polynomial time predicate or as a circuit. And you have to, so meaning that you are not able to efficiently just traverse this whole graph in order to find a solution. Yeah, so you have to use other ways. So it's an exponentially sized object. Okay, so that's kind of the classical setup. here in this talk, I want to, so we want to guarantee totality by theories like boundary arithmetic and or pair arithmetic. Okay, so now I managed to pass my introduction and I have 20 minutes left to show you some of the results. So, okay, let's look at some of them. Okay, one thing which I should say here is you can compare problems in a natural way simply by looking at reducibility, like many one reducibility as you use in other places as well. And it's the natural way, so you say P is reducible to Q if you want to use Q in order to solve P. So you have an input P, you map that input to Q with F. You find a solution for Q, which you then transform into a solution for P. If you are able to do that with P time functions G and F, then you say that P is reducible to Q. And we will kind of look at classes of total NP search problem in this way. And I forgot that I wanted to now just give another motivation at this point, why it is an important problem. So if you take as TF and PT for theory T, the set of provable total NP search problems in T. And by that I mean, so the totality aspect, so you need to be able to formalize, you need to find a sigma B1 formula defining the polytime function, the search problem, and you need to be able to prove totality in this theory T. Then we say these are the total NP search problems of T. And if you look at this hierarchy, this increasing hierarchy in probability strength of boundary arithmetic theories, and look at its total NP search problem, it gives you an increasing chain of classes of total NP search problem. This is simply because the probability strength increases. You have more and more power to prove totality. The stronger theories can prove the totality of the weaker theories. Therefore, you have this increasing chain. But nothing stops you at boundary arithmetic. You can go beyond boundary arithmetic. You can also look at I sigma 1 and think, okay, what provable total NP search problems does I sigma 1 prove, or Peano arithmetic, or go to ZFC. Yeah, and you get an increasing, potentially increasing chain of total NP search problems. Of course, the question is this hierarchy strict anywhere? So can you show that the total NP search problems of ZFC are stronger than FP? Of course, easy to state, but if you are able to prove that, you would solve P versus NP, because this is intermediate between FP and NP intersect co-NP. Yeah? So it's not an easy question. If you believe that maybe it should stop at some point, then we would also get an interesting result. Namely, we would get a characterization of all total NP search problem in a syntactic way, which currently we don't think exists because it's kind of semantic class. So the belief is that there is no syntactic description of TFNP, of the whole class of total NP search problem. Okay, now let's look at some total NP search problems in boundary arithmetic. And I want to start with a polynomial local search. So that's an extension of the polynomial local search problem, which we have seen before. And it's now made a little bit more complicated, but that allows then to relate, to characterize various levels of total NP search, provable total NP search problems in boundary arithmetic. So how does, what is a PyBK polynomial local search problem? So you have this F is your search space, this exponentially large search space, and the X is your input. You have, in this setup of polynomial local search, you have a function I, which gives you an initial value. It just points to some point in your search space. You have a neighborhood function, which maps points to points in your search space. It may map to itself, it may loop. And you have a cost function. Yeah, so each point in your search space has a cost via this function C. And then the condition is right, and I didn't write it here. So the neighborhood function, if it doesn't loop, will you produce a potential solution of lower cost? Yeah. And the search task is find a point in this search space where the neighborhood function is looping. And why can we always find that? Well, that's induction, right? So or minimization. So each point has a cost. Those points with minimal cost, on those points, the neighborhood function has to loop because it can't produce a point with lower costs anymore. Yeah. So kind of the setup gives you a guarantee of totality. You could also view this as a directed graph given by the neighborhood function up to those deep looping points. But that's kind of the guarantee which guarantees you that you find a solution. Now, all the ingredients I, N, and C, they are polynomial time computed. The search space itself now is not only polynomial time computable, but it's higher up in the hierarchy of polynomial time computable predicates. So it's in pi bk. So you can write this down formally, but I won't skip this. It's exactly the same explanation, the same thing which I just explained in Word, written more formally. Just as a remark, if we take for f just the p-time functions, then you get exactly PLS as we had before, polynomial local search. What are the results? So the first one is that it goes back to Bus and Krajicek from 95, is that the provable total NP search problems of T12 are exactly the polynomial local search problems. So that's one level up. So for S12, we had that it is FP, the function computable in polynomial time. For T12, the next stronger theory, we get PLS. And that can, so if we then look at pi bk PLS problems, then the statement of a solution is a provable total, that the solution exists, is a provable total NP search problem in tk plus 1, so that extends the result from Bus and Krajicek. And I don't go into the proof of that. I just state the final result that the provable total NP search problem of tk plus 1, 2 are exactly characterized by these pi bk PLS problems. Okay, so now we have a characterization of provable total NP search problems for all levels of the polynomial time of the boundary arithmetic theories, in a sense, if I just focus on the K2 classes. I should mention here that other characterizations were also known. So colored PLS is a similar version to this pi b1 PLS, and then Kolochevich, Skelly, and Tarpan had this characterization for T22, similar to what Sam and I have. And Skelly and Tarpan also had other principles like the game induction principle, which is a K-turn two-player game based on induction, which also characterize exactly the total NP search problems for TK2. So there are various characterizations, trying various combinatorial principles which characterize exactly those levels of the total NP search problems. Right. Am I over? Oh, 10 minutes. Okay, good. Good. So then let's skip over those. Let me just say that there are also local improvement principles which are able to characterize. So they are kind of so you have an infinitely large structure, a graph, and you have a way of locally, so they a labeled graph, and you have a way of improving the label set of those graphs. And depending on the structure and the number of rounds, you can also characterize all levels of total NP search problems for all theories of boundary arithmetic. another characterization with a different structure. Maybe just, and I won't go into details of this one because I want to explain something else. Let me just skip to the result. Right. Here we go. So, so I was about to explain Frege and extended Frege proofs. So Frege proofs are propositional proofs in a standard propositional system, as you all know it from your studies. And extended Frege proofs are an extension of those standard proof systems with the extension rule. So you're allowed to abbreviate formulas with propositional variables, which allows you to write proofs more succinctly. So these are two very important proof systems studied in propositional proof complexity. And it's still an open problem whether they have the same class of polynomial sized provable consequences or not. Here we turn those proof systems into a search problem. Namely, if you think of Frege proofs, if you have given an infinite, no, not an infinite, but an exponentially sized Frege proof of contradiction, the search task is to find a place of inconsistency in this Frege proof. Yeah. So you have an exponentially sized proof given, for example, via a secret to you. It ends in a contradiction, but otherwise it starts with correct axioms. There must be something wrong in this proof. So find this place, point at this place where it is wrong. So that's the Frege consistency search problem, and that is a problem which is complete for U12. So the theory linked to P space. And if you go to extended Frege proof, so the same problem for extended Frege proofs, then you get something which is complete for V12, which is related to X type. Now, Goldberg and Papadimitriou have a similar search problem, which they called wrong proof search problem. It's a little bit more general than boundary arithmetic, and it's a bit unclear also how it relates to those U12 and V12 system. But in nature, it's the same. It's a propositional proof system, bit richer than boundary arithmetic or the standard which I have. And again, you look at exponentially sized objects of a proof of contradiction, find the error within that proof. And the standard TFMP problems, which we saw at the very beginning, they are all included in those consistency search problems. They are kind of the strongest natural ones which we have here. Now let me, for the remaining 5 minutes, speak a bit about what you can say about total NP search problems of Peano arithmetic. So, let me just describe a characterization of those. So you do a similar setup as for the polynomial local search problems, except that this time this space can be really big. So you start with a set of possible solutions again, which can be much bigger than polynomially, it doesn't need to be polynomially bounded. You are looking for, you again have this neighborhood function and you're looking for solutions. But now you have a guarantee that whenever you found a solution, this solution is actually polynomially bounded in your input. So you're good there. And then you have the same setup. You have an initial value, you have a neighborhood function, but now you have you have a cost function which takes you into into a well ordering, into an ordinal. Yeah. And now the cost function simply produces values such that when the neighborhood function is not looping, it produces a value of a smaller value in this ordering here. Yeah, and the search task is to find an S such that the neighborhood function loops. Yeah, and again, totality this time is given because we have here a well ordering. Therefore, you can look at the values, the minimum values according to this well ordering, and according to this setup, it has to loop. Yeah, so therefore it is a total NP search problem. And I'm not going into the technical details, but just let me state the theorem. So any such problem is actually a total NP search problem. In order to speak about that, you need to formalize it, and formalized such search problem is one in which all the predicates are given by appropriate formulas, so they're polynomial time computable, and the conditions are all provable in this weak theory of bound arithmetic. And if you take that, then you can show that the provable total NP search problems of Peano arithmetic are exactly characterized by such alpha BLS problems. So where the ordinals, the well ordering is given by ordinals or some well ordering system related to such ordinals for any ordinal less than epsilon 0. Yeah, and that kind of resembles or is kind of similar to the characterization of the provable recursive functions as we have seen at the beginning. Good. I won't go into the details of that proof. For those who know ordinal analysis, so it simply is the direct way of translating Peano arithmetic proofs into infinitary proofs, applying cut elimination, and then looking at the path from your final formula and trying to find the witness. The essential part is this paper, which I had with Klaus Ehrlich, that if you do that, then anything, the neighborhood function, anything which you look at there is actually polynomial time computable. That's the interesting bit which you need in order to get the setup. Okay, so much for that. Let me just conclude one point how this setup can be used is that if you take those principles, those descriptions, you can often turn them into hard principles, meaning that if you describe everything generically, all your polynomial time functions, etc., describing this principle, if you describe them with oracles, you get something which is a generic principle, also of this form of that is for all sigma b1 formula, and it's usually complete for the system which you're looking at. And we didn't speak about proposition proof complexity. You can translate it into proposition proof complexity, and there you get the hardest problem in that setting. There are some other results currently going on which link TF&P to proposition proof complexity and circuit complexity. It's really seen currently. So first, there are more and more results for TF&P coming out by looking by taking a view on propositional proof complexity, in particular also getting oracle separations. The other thing is that TF&P is viewed as a unifying principle to look at to provide connections between proposition proof systems and circuit complexity. Yeah, but I'm just pointing to this paper. Actually, I also haven't fully understood what is going on there, but a lot of people are now working on these areas, and it's really exciting to see that. Let me just finish with a couple of open problems and future work. So the first one is what I spoke to about before, right? So take those TF&P characterization, turn them into propositional tautologies via these generic principles, and prove lower bounds related to those propositional proof systems. So this is a really hard problem. We are kind of in propositional proof complexity, struggling to come up with good combinatorial principles which allow separation of propositional proof systems. There are results, but progress is quite limited. Yeah, and this could be a potential source. But I have to say, the combinatorics of those are usually quite hard, and it's really hard to work with them. So one may need different type of characterizations. In particular, separate T22 from T32. Currently, we are able to with it for all sigma b1 symbols. Yeah, so I said that we have separations coming from separation of complexity classes, but they usually increase in the complexity. We don't have separations on for all sigma b1 setting, in this relativized oracle setting. So I'm not speaking here about full separation. So try to do that between T22 and T32 in any way. Analyze TF and P for other theories, like I did for piano arithmetic. Yeah. So my conjecture is that any theory which has a good ordinal analysis should be able to get a characterization of the provable total NP search problems. The challenge will always be to be sure that every local thing can be described with a polynomial time operation. Yeah. So there may have to be some challenges in the ordinal notation systems which are used, but usually from what I could see, this is usually given that those are efficiently computable. Find better characterization. So current one is really brutal ordinal analysis, what I'm using there. Are there other characterizations which you can find, which are of more combinatorial nature? And finally, find interesting combinatorial principles in relation to TF and P, maybe based on other areas of computability, things which have been discussed here at this workshop. And here I'm coming to the end. Thank you. Probably out of time.
Thanks, very nice talk. We have some 5 minutes for questions. Are there any questions? Yeah. I'll go over to
Thank you.
So yeah, this area is outside of my expertise. Also early in the morning.
And after the conference dinner.
Yes, that too. Okay, so this actually is more about the earlier part, I guess, the more of the background. So this is not really a well-formed question either, but I'll say it anyway. So I was seeing you talk about, you mentioned the smash function, you mentioned all these complexity classes. My brain went to Cobb's thesis, fragments of recursion and characterized complexity classes, Anthony Cook. And while I was listening, I looked up some of these things. I even stumbled on the Stack Exchange discussion about whether Anthony Cook's result from 1992 has any relation to Cook. What was that name? Krakow? No, I know Rakov. What was the name?
Rekov?
Rekov.
Yeah.
And I didn't have time to read the answer, but it seemed the answer was not very much. But I was drawing these associations as you were going, and then okay, your main results went kind of in a different direction. But is there any connection between these topics, or not? And if the answer is no, that's fine. This is outside of my area, but yeah, I drew these mental connections. I wanted to know which one needed.
There are connections, and actually, in my PhD, I looked. So my PhD, I tried to incorporate the work of Anthony Cook and the typing in order to characterize classes of characterized polynomial time, into the boundary arithmetic setting. So simply try to come up with two sorted theories which extend the work of Anthony Cook. I had some results, but no further deeper connection. Yeah, you get statements about this delineation, but you're not getting strong results back to pure complexity if you forget about delineation. Yeah. So it's about if you look at algorithms where you said, okay, I delineate the algorithms according to the typing of Anthony Cook, you get strong results. Yeah. But that is restricted to that you said, okay, I restrict the arguments according to this normal and safe parameters, but I'm not getting back to algorithms which then have no typed inputs. Yeah. So that was my take on that side. Yeah. So I got some beautiful results. But in the end, this more structural way was not able to answer questions we cared about in this more general setting of complexity theory.
Thank you.
It's something.
That's exactly the answer. Thank you.
Yeah, thanks.
Further question? Yeah.
Thank you, Arnold. It's a great one. I was wondering about the role of business in this approach. So, like, for instance, for subclasses of these PFP, I mean, like, besides the cases you gave, are you going? Do you expect that somehow finding completeness is going to be any easier than the usual machine models? And if it is, I mean, how important it is? I mean, does it? I mean, in the classical definition of complexity classes, completeness is very important for many different reasons. The importance is not that much because kind of the characterization is more important than the characterization of the class itself.
Can I check? So with completeness, you mean complete problems in a complexity class?
Yes. So it's finding complete problems.
Yeah.
Or it's
no,
their significance. Is it any different?
No, it kind of, it is implicit. It's all about the complete problems, right? So so for example, the initial classes which Papadimitriou defined, where he just gave a combinatorial principle, like PLS, yeah, let's take PLS, and then simply said, okay, we take the complexity class which takes this as a complete problem, we close under reduction, so then by definition it is the complete problem, and that is the class which we care about, and that's kind of what then gives you kind of a zoo of complexity classes with complete problems. And the question about complete problems in TF&P is definitely an important question, but it's also for this connection. Like when I say that I want to characterize the class of provable total NP search problems of a theory, I really aim for finding a complete problem for that class. Because that complete problem, and that was kind of the thing which I hinted at the end, right? So you can get to that if you kind of look at it in a generic way. Then you get the complete problem, because that allows you then to use that problem and look at it in other settings. You know that it will be, because the theories are kind of connected to certain classes of propositional logic theories, which we try to separate. If you take the complete problem, translate it into a propositional tautology principle, then this will become the hardest problem, the complete, in a sense, for propositional logic problem within that class, and can be used in order to separate it from the weaker one. That's at least the hope. So yes, complete problems are key in the study there.
Well,